Today we will learn about the summary of ATP synthesis from the oxidation of one molecule of glucose. Here glycolysis occurs in cytoplasm, glucose to glucose 6-phosphate. Here NADS and FADs and a loss of 1 ATP occurs. Then in fructose 6-phosphate to fructose 1,6-biphosphate, where also loss of 1 ATP occurs. In 2-glyceraldehyde 3-phosphate to 2-glycerate 1,3-biphosphate. These two NADs are formed. In 2-glycerate 1,3-biphosphate forms 2-glycerate 3-phosphate. Here 2 ATPs are formed. Then 2-phosphophenol pyruvate, it forms 2-pyruvate, and here 2 ATPs are formed. The mitochondrial reactions: 2-pyruvate to 2-acetyl coenzyme A, it forms 2 NADs. In citric acid cycle, 2-isocitrate to 2-alpha ketoglutarate, it forms 2 NADs. 2-alpha ketoglutarate to 2-succinyl coenzyme A, it also forms 2 NADs. 2-succinyl coenzyme A to 2-succinate also forms 2 ATP. 2-succinate to 2-fumarate, it forms 2 FADs2. 2-malate to 2-oxaloacetate, it forms 2 NADs. Now here total 10 NADs, 2 FADs2 and 4 ATP molecules are produced. Total yield of ATP from the complete oxidation of one molecule of glucose by glycolysis pyruvate dehydrogenase complex reaction TCA, citric acid cycle, and oxidative phosphorylation, its total is 32 or 30. This is calculated as 2.5 ATP per NADS and 1.5 ATP per FADS2. Total number is either 30 or 32 depending on the mechanism used to stir NADS equivalents from cytosol to mitochondrial matrix. P/O ratio. Under aerobic conditions, each mole of NADS or FADS2 carries 2 electrons and each 2 electrons reduce 1 atom of O. Therefore, under aerobic condition, ATP production from oxidative phosphorylation with oxygen as the electron acceptor can be equated to the electron transport or atoms of O consumed. The ratio of ATP produced to E electron released or atom of oxygen consumed may be defined as P/O or P/2 electron ratio under aerobic conditions. Now, respiratory quotient and respiratory substrate. Respiratory quotient is the mole of CO2 produced divided by moles of oxygen consumed during complete oxidation of a metabolic fuel to CO2 and H2O. Carbohydrates such as glucose, the RQ is given by CnH2n ON plus NO2 forms NCO2 plus NH2O. Number of molecules of O2 consumed to the molecules of CO2 produced. We have a ratio of 1 to 1. Since there are NO2 and NCO2 molecules, so RQ N by N is equals to 1, and for glucose RQ 6 by 6 is equals to 1. RQ is less than 1 when respiration is aerobic, but respiratory substrate is either fat or protein. RQ is about 0.7 for most of common fats and about 0.9 in case of proteins. For palmitate, RQ is given by 16 mole of CO2 produced divided by 23 mole O2 consumed is equals to 0.7. RQ is more than unity when organic acids such as oxalic acid, malic acid are broken down as respiratory substrate under aerobic conditions. Now, catabolism or breakdown of dietary fuels occurs in 3 stages. In stage 1, breakdown of large molecules of fat to simple building blocks. Carbohydrates in form of polysaccharides are broken down to simple sugars such as glucose. Proteins are converted to amino acids. Neutral fats are converted to free fatty acids and glycerol. In step 2, breakdown of simple building blocks to acetyl coenzyme A. In stage 3, complete oxidation of acetyl coenzyme to CO2 and water with the production of ATP. This is the simplified diagram showing the fate of respiratory substrate.